It has all the qualities of an aircraft.
How's it certified? Just like an aircraft. What infrastructure does it need? Same infrastructure as an aircraft. It needs a runway. So how does it launch? Yep, just like an aircraft.
But equipped with the performance of a rocket, the Dawn Mk2 Aurora isn't your standard 707 jet.
In the space of about 6 or 7 flights, we went from pretty low performance flights, flying not that high, not that fast, 200 knots, 9,000 feet, to supersonic and 82,000 feet.
Kia ora, I'm Davina Zimmer, and today on The Detail, I'm in Christchurch to learn about sustainable space transportation and a suborbital spacecraft on a mission.
We have a real path to this being the first vehicle that flies to 100 kilometres altitude, the border of space, twice in a day. No one's ever done that.
That's Stefan Powell, one of the co-founders of Dawn Aerospace, a Kiwi startup working on developing greener and more convenient alternatives to traditional space transportation. Let's start with how it started, a group of university students with a goal.
We decided we wanted to break the European altitude records for suborbital rockets, so we got together and we started building really quite big rockets. So to do that, we actually needed to develop new propellants that were appropriate for students to use, because rockets are generally pretty complicated. They're generally using exotic things like liquid oxygen and, that's cryogenic, so that's super, super cold, really hard to deal with. So we actually ended up developing entirely new classes of rockets. We spent about 5 years doing that. We raised our own money. We got these big rockets built. We managed to convince a Spanish military base to allow us to launch that out over the Strait of Gibraltar.
How did you manage that?
Yeah, it really is just a process of starting small and iterating and getting more advanced, like bigger and bigger as you go. It's just taking many, many small steps. And each step is not really huge. It's just a bit beyond what you've done. And because it's just a bit above what you've done, you can kind of convince people like, hey, look, I know what I'm doing. Let me go just a little further.
In 2015, they launched a 1.3-ton rocket from a Spanish military base, breaking the European world record. This was during a time where satellite launching really started ramping up, and it's here where Stefan and his fellow students noticed another issue.
There was this real excitement, but there was also this tension in that, the underlying infrastructure, like how to get to space, the way that satellites are built and whatnot, it's actually not really ready for all of this potential. Like, we're not going to reach this potential unless we change the way that we get to space and the way that we move around in space. It was like the toxic fuels that satellites use, like hydrazine. Like a teaspoon of hydrazine in this room will kill everyone. It's just that gnarly and toxic. It's a great propellant, don't get me wrong. Like, it's worked super well for 70 years now, so there's a reason that they use it. But it's mostly militaries and governments and whatnot that have billion-dollar budgets that can deal with this sort of level of toxicity. But now it's Silicon Valley companies that are wanting to use this stuff. They want to use it on hundreds, if not thousands, of satellites at a time. So if any one of those satellites leaks, it's a problem. And ultimately, risk of failure is a statistical game, right? It's a 1 in 1,000 or 1 in 100 chance that your satellite leaks. So when you've got 1,000 satellites you want to launch, it's like, statistically, one of these is going to leak, and that's going to be a massive problem. So we had to change to propellants where leaking was acceptable, where you could have these minor failures without it, causing death, essentially.
So in 2017, Stefan and his 4 co-founders began their next mission, figuring out how to make space transport greener and cheaper.
So, if we talk about the cost of getting to space, the main cost is in the manufacturing of the actual thing that you fly, the rocket. As of 5 years ago, they basically exclusively got thrown in the ocean. They were all single use. SpaceX is making great strides. I think they're up to reusing about 20 times now. So that's already a lot better. But still, that's not really what we would call reusable. If you could only use your car 20 times before it was completely toast and you had to buy a new one, you probably wouldn't be that happy about that.
Yeah.
They're also not reusable in the sense that you just go up to them, turn the key and fly. So what we're trying to do is make, getting to orbit, or getting, at least to start with, up to suborbital heights, 100 kilometers altitude, show that we can do that with something that's truly an aircraft, and that it operates like an aircraft, it's licensed like an aircraft, it flies from existing infrastructure like airports, and is something that you can truly use multiple times a day, just like you would any other aircraft.
Enter the Dawn Mk2 Aurora. It looks like a plane, and in many ways it is, until it takes off.
Normal aircraft can only take off at about a 20 to 30 degree angle because that's just as much power as they have. We're a rocket in the sense that we have a rocket engine, and as we burn more propellant, we get lighter, and our rocket engine actually gets more efficient as we go higher. So you can start going to extremely steep climb angles. So we're climbing at 70 or 80 degree angle. We're basically going vertical, and we just go faster and faster and faster as we get higher and higher.
So in many ways it's like a plane. One way that I can see that it's not like a plane is I don't see a cockpit where a pilot can sit.
Yes.
Can you explain that to me?
Yeah, absolutely. So that's one of the beauty of modern aircraft is that computers are getting better and better. The software that actually run them is really good. Most planes that you would fly in these days, like a 787, can actually entirely fly itself. The pilot is more or less there for a certification reason. Now we can go one step further than those planes and just take the pilot out of the cockpit and have them sit on the ground. So that's great from a risk perspective because my safety concerns are not so much for the vehicle itself, it's only for things on the ground. So we can take much more risk if we're not actually concerned about the life of the vehicle, if you like. That's a financial penalty. The things that we really need to insure for is people on the ground, people's homes or whatever that we're flying over.
The aircraft is still controlled by a pilot who's set up in the back of the same trailer that's used to transport the aircraft on the ground. It's set up with several screens streaming video footage from the cameras on the Aurora. As well as a pilot, there's also a flight director and a navigator who makes sure the plane is staying in its designated airspace to avoid any collisions. Dawn's first mission was to fly the aircraft to suborbital level twice in one day. They ticked that off last September. Now it's about going bigger and better.
There's not really too much point in just repeating what we've done. So it's really dependent on how long does it take us to do the next upgrades on the plane. We're now working on an upgrade of this vehicle which requires us to rebuild the airframe, so we'll build a second whole vehicle. But aerodynamically it'll be the same. Because the point of this first vehicle was to show that we could fly supersonic. There's a whole lot of really challenging things that happen around breaking the sound barrier. Lots of non-linear effects and crazy things that make your structures vibrate or your control surfaces flutter or do funny things. So we wanted to show that the aerodynamic design of the aircraft was good. Now that we're sure of that, we can build the full performance version of this, which will have more propellant on board, higher thrust engine. It'll have a reaction control system to allow us to orient the aircraft once we're out of the atmosphere. Because once you're out of the atmosphere, your elevators and rudders and whatnot don't work anymore, right? Because there's no air.
Yeah.
So you need a way to control the orientation of the vehicle before you re-enter the atmosphere. But ultimately that upgrade package will then allow us to fly to space twice in a day. We'll get to 100 kilometers altitude, which is like 4 times higher than any aircraft has ever flown. It'll allow us to fly to about Mach 3.5, which is faster than any aircraft taking off from a runway has ever flown. The only aircraft, if you like, that have ever flown faster than this are ones that are not really aircraft in the traditional sense. They're like the space shuttle. Like if you call that an aircraft, that's flown faster, but it doesn't take off from a runway. X-15 or Virgin Galactic's vehicles, they might fly faster, but they're all launched from other aircraft. So the problem with that is they don't have the business model of aircraft. This will be the first time something that truly operates like a traditional aircraft is getting rocket performance. And that opens up so many new markets for us that allows us to do things that no one's ever done before. There's lots of really interesting applications in being able to fly to space twice in a day.
Correct me if I'm wrong, but the purpose of being able to fly to space with this is to transport stuff to the International Space Station.
So eventually, you do want to go to orbit. That's always been the dream, right? What we're actually finding now is people are saying, well, this vehicle that you actually developed as a technology demonstrator, actually I would love to use that to develop my satellite technology. I have a fancy new camera that I want to put on a satellite, but I don't actually want to put it on a satellite to start with, because then it's up in space and I can't get it back. Can you just fly me up way above the clouds, to a satellite-like altitude? I want to take a few photos, show that camera works, and then I want it again so I can change some settings and do it again. So ultimately we're helping them develop satellite technology without going to orbit. So there's a great application. There's people in the pharmaceutical industry that want something called microgravity. So they want this zero gravity effect because physics is just different in microgravity. You don't have convection, like heat rising doesn't happen in space because there's no gravity for, the lower density thing to rise. So sedimentation processes are different. Crystal formation is different, which means proteins grow differently, which means I can develop totally new drugs. They can make ibuprofen that's like 1,000 times more effective just by having a different way that the crystal forms. They already go to the International Space Station for that, but that's, tens of millions of dollars per test that they want to do. It takes years to actually get on station and then years to get your sample back and show, did this test work or not? But with us, they'll be able to fly multiple times a week at much, much lower cost. They'll get that microgravity for 3 minutes at a time. They can run their test and show, did it work or not? If yes, let's test the next thing tomorrow.
So do they give you a little box of something?
Yeah. So this vehicle has a payload bay on it. So essentially that's an area on the aircraft here where they can slot their test in.
Okay.
So, that might be like a biomedical test where they crystallize some proteins. Atmospheric scientists might want to access that upper bit of the atmosphere to let them take atmospheric samples at say 40, 50, 60 kilometers, parts of the stratosphere that we know affect our weather on the ground, but nobody really knows very much about it because we just don't have frequent access to it.
But this Aurora space plane is only one part of what Dawn Aerospace is working on. The other part is satellite propulsion. Everyone
was using hydrazine or using electric propulsion. Hydrazine is toxic and electric propulsion is quite slow, so both are restraining in different ways. For about $1 million, we developed these new propellants, nitrous oxide and propylene, self-pressurizing gases, very simple, spark ignited, even refuelable in the future. That was something that we could start providing to the more forward-leaning startup companies out there who really wanted a new technology.
Shall we go have a look at these propulsion pieces? So what room are we in now?
Yep, so we're out in the workshop. You said you wanted to see some satellite components, so we've got plenty of them out here. Yeah, we build satellite components for over 20 customers now, and we're producing about 5 thrusters a week here. So out here on the bench we have essentially a mock-up of a propulsion system. So, a propulsion system consists of thrusters, control systems, feed systems, and whatnot. The feed systems need heaters, the thrusters need power supplied to them, they need signal to, for them to know when to turn on, and the control system talks to the satellite's main computer. The pipes supply propellant from the tanks, which are in the center of the propulsion system.
So would they sit here?
Exactly, the tanks. Okay. So one over here on this table.
They look a little bit like those, like the cream canister nangs.
Yeah.
But
exactly.
just like a big version of them,
yep.
And that will sit in the middle of this square plate with these pipes around it, and you'll connect it to these pipes, and that will feed whatever's in here all around.
Yeah, exactly. That feeds oxidizer, which is nitrous oxide, and the fuel, which is propylene, to the thrusters, because each thruster needs, essentially air, fuel, and an ignition source. So it's just like a car engine in that sense. The only difference being we can't breathe air from the atmosphere because there is no atmosphere in space. So you've got to bring that atmosphere with you. Right. That's the nitrous oxide. You still need fuel, of course. Cars use petrol. We use propylene, which is basically barbecue gas. And that gets injected into the thruster, ignited and burns, and that generates thrust. So this is everything that a satellite builder needs to give their satellite mobility. In software terms, they get a big red button that says push here for thrust on thruster 1, push here for thruster 2, 3 or 4.
Yeah.
Push it as you desire to make your satellite move. We control the temperature of the system, we control all the valving, so it's really, really easy for satellite builders to use our system.
So if you create these systems and you sell them to someone, once you hand that over, is that your job done?
So there's a lot that happens once you hand over that propulsion system. It has to get integrated, it has to get tested, then it goes to the launch site, and you have to fuel it up, and then it gets launched into orbit, and then they want to make sure that it all works. There's lots of things that you can't test for on the ground, like you don't know, especially the thermal environment of space is quite strange in that you have the sunny side is actually really, really hot because the intensity of the sun in space is really high, but then the side that's not facing the sun is radiating to the blackness of space, which is really, really cold. So you'll have extreme thermal gradients through your satellite, which can do funny things in a propulsion system.
Yeah.
So managing that is something we help them, learn. At that point, they should be able to use their satellite propulsion system by themselves.
These propulsion systems can be used for a variety of purposes, but the most common one is in satellite constellations.
They want to provide communications to people on the ground, so they want to have a satellite overhead at all times, right? So they need many, many satellites to do that, because the satellite goes overhead, it'll see you for about 6 minutes, and then it's gone, and the next one has to come. So all these satellites have to be properly separated, but they all get launched in one big clump. Some people might have even seen it as these Starlink trains going by in the night sky,
Yeah, I do
right?
remember that, yeah.
That's how they get launched. So they have to separate themselves, and they do that using a propulsion system. The first one will go forward, and the back one will go backwards, and they progress their orbits.
So they self-drive, essentially.
Yeah, exactly, into position. So you need a propulsion system for that. But we've also had customers that, that want to go out to the moon, so they need propulsion to, transfer that orbit to then be captured by the moon orbit. They have to slow down again to go into that lunar orbit and then manage their orbit while they're at the moon. Once again, you need propulsion.
Yeah.
So yeah, lots of reasons that you would need propulsion. Some need lots of it, some need not so much. Every satellite's a bit different. So we have to also be really good at customizing our systems to meet those different needs. The constellation builder needs a relatively small propulsion system because they're mostly just sticking around Earth. Our customers that are going out to asteroids and want to do asteroid mining, they need a lot of propulsion. So like 80% of their satellite is propulsion. Exactly.
And this one's obviously, it's not massive. I mean, it's about 40 by 30. How big or small can you make these?
Yeah, so we have ones that are for what we call CubeSats. The entire satellite is about the size of a milk carton, and the propulsion is about a third of that, so tiny. The largest is hundreds of kilograms. But generally, satellites have gotten a lot smaller over the last 10 years. They used to be these big monolithic, 3 to 10 ton things, and they'd have obviously huge propulsion systems on board. Very capable single satellites, but also limited in the sense that it's just one satellite. Satellites are generally moving towards being what they'd call a distributed system now. So where the job that they would have done with one satellite, they'll now do with 100. So I can tell you a little bit about how they get made.
Yeah, please. What Stefan shows me next looks a lot like a metal shot glass set on top of a chunky plate with several holes in it. There's also a small pipe running up the side connecting the base to the shot glass. This is a thruster in its earliest form.
So it's 3D printed in Inconel. So it's a high temperature alloy, but it's not super fancy. It's thrusters used to be made out of what they'd call rare earth metals, so like platinums or niobiums or like really, really expensive metals. These are much lower cost to produce because all the complexity is in the design, not in the manufacturing. You can see a whole lot of tubes running along this thing. This is a regeneratively cooled thruster, so there's one tube that goes down the side that then supplies a complex network of channels inside there before the propellants are actually injected into the combustion chamber. And then spark plugs ignite the propellant, and then you see this big shot glass looking bit, the divergent nozzle. That's where the thrust is actually generated. The hot gas is converted into fast gas.
The gas goes in through the pipe starting at the base and gets fed through to the other end, the part that looks like a shot glass. The smallest thruster in the workshop is only 100 grams, which is pretty tiny, but Stefan says satellites don't need much more because not a lot of power is used once they're in orbit.
Yeah, they're really just looking for tiny, tiny pushes. They'd only turn their rocket motors on for 5 seconds at a time, and that's enough just to adjust their orbit because they're not really trying to do massive changes. They just want a tiny little push in the right direction just to trim it.
Once the 3D printed rough cut is trimmed down, it's off to the cleanup and assembly station for stage 3.
So this is a hyper clean environment where we have filtered air flowing down. Our nice clean thruster goes into that environment and then gets mated up with valving basically. So valving is what controls the flow into the thruster. It also gets an electronics box with the high voltage like spark generating circuitry on it and a spark plug. And then out the end of this bench we get a fully assembled thruster, which is then ready to be tested.
And it's done so that there's no dust that can go in. Why is dust bad?
So the valving and the thruster itself has lots of very, very small geometry in it. There's holes in there that are sort of on the order of 1/10 of a millimeter in diameter. So you'd think 1/10 of a millimeter is pretty small, like this is much smaller than like a grain of rice. So any little particle has potential to block that or alter the flow and then alter the performance of the thruster.
Right.
So we want to make sure that it's as clean as possible in there. to make sure that that thruster is going to operate the way it should.
And so then from there, is it ready to be, I guess, packaged up and sent out?
In high volume manufacturing, yeah, you would be able to just send things out, but in space, people want to make sure that their products really work, and the only way to really know that it works is to show that it works.
Okay.
So we have to take it into this room here, which is where we test all of our thrusters.
So this is what the cylinder is?
Yeah, to simulate the vacuum of space, we put it in this cylinder. This is a vacuum chamber where we can pull a vacuum on it. We've got a vacuum pump that sucks all the air out. And then we're able to actually show that the thruster works. So each thruster will do about 400 burns to show that it ignites reliably, and we'll do that at several different operating points. The thruster has a lot going on in terms of fluid flows, so whether there's pressure outside the thruster or not affects how the thruster works. That's one element of space that we have to simulate. But they're not so sensitive to gravity, they'll work in any orientation. The thruster doesn't care about that. The other aspect of space that we have to simulate is the temperature. So the propellants in particular are sensitive to temperature. It's kind of like barbecue gas. If you've ever tried to run your barbecue on a really, really cold day and it doesn't work very well, that's a potential problem in space. So we have to show that it works at the minimum operating temperature, but also the maximum operating temperature.
So how do you show that in here? Because this is obviously like a fridge.
Yep.
And do you just chuck it in there and leave it for a bit and then test it?
Yeah, so this fridge is essentially the space environment that allows us to make it really, really cold. And then the tanks are basically simulating what happens in a real satellite, in that we have tanks, and those tanks have heaters. So it's to show that heating the tanks in a cold environment still yields propellant conditions that are acceptable for the thruster.
So the fridge is acting like space.
Yes.
And then these tanks in here act as the satellites.
Exactly.
Okay.
Yep.
Dawn Aerospace is now 8 years old, operating with over 120 employees across its headquarters here and in the Netherlands. Breaking into the industry wasn't easy, but now they've proven themselves, Stefan says they're in good shape.
It's a challenging business to do a startup in, because the gap between having an idea and having a product that you can sell is big. And then even the gap from having that product to proving that it works, which is usually the point at which people actually want to buy, is massive. And then even when you get there, the gap between having the first people buy and being able to deliver it at scale to a point at which you'll be profitable is even larger again. So that the first few steps are kind of 10% of the problem, and then the manufacturing part can be the other 90%. I think like Elon Musk and Peter Beck have famously talked about this.
Yeah.
For Dawn, manufacturing propulsion systems at scale is a real challenge. Like, this is just genuinely a hard problem that multi-billion-dollar companies even struggle with sometimes. The reward is that when you get there, you have this incredible business moat. You know how hard it is to get there, and you know how hard it's going to be for anyone to follow you.
That's all for today. The Detail is a newsroom production supported by RNZ and New Zealand On Air. Thank you to Stefan Powell. This episode was engineered by Jeremy Ansell and produced by Gwen McClure. I'm Davina Zimmer, ka kite anō.